Every structural element exists to transfer external loads to stable foundations. Structural analysis is the process of tracking exactly how those external transverse loads translate into internal stresses before they ever reach the supports. That translation is dictated by boundary conditions. Determinate beams, like simply supported, cantilever, and overhanging beams, can be resolved using the laws of statics alone, while indeterminate beams require us to account for how the material itself deforms. These external forces manifest in 4 loading profiles: point loads acting at a specific coordinate, uniformly distributed loads spreading evenly, uniformly varying loads that increase linearly, and pure rotational couples. Identifying these boundaries and load profiles is the mandatory starting point for any analysis of internal stress or structural failure. Our sign conventions are grounded in tension. A positive bending moment creates a sagging smile, stretching the bottom fibers. A negative moment causes a hogging frown, stretching top fibers. For shear, left up or right down equals positive. We connect these forces using the calculus staircase. Internal forces are mathematical derivatives of external loads. To find the internal shear force, we integrate the load. To find the bending moment, we integrate the shear. This master curve matrix shows how those integrals translate into geometric shapes. As you move from load to shear to moment, the degree of the polynomial increases by 1 step, meaning a constant load becomes a linear shear force and a parabolic bending moment. These mathematical relationships provide the framework for analyzing the combined effects of various loads across a structure. On a simply supported beam with both a point load and a distributed load, we map the vertical forces to generate a shear force diagram. Notice how the point load creates a sudden step, while the distributed load creates a linear slope. By calculating the area under the shear force curve, we determine the vertical height of the bending moment diagram at every point along the span. Notice the direct correlation. The slope of the bending moment diagram at any specific coordinate is equal to the height of the shear force diagram at that same point. Applying a pure couple to a cantilever beam illustrates a specific behavior. The bending moment diagram shows a sudden vertical step, but the shear force diagram remains completely flat because no vertical force was added. External couples generate immediate rotational stress without changing the transverse shear force within the beam. In an overhanging beam, distributed loads create simultaneous sagging in the middle and hogging over the supports. This results in a bending moment diagram that transitions between positive and negative regions. Pay close attention to the coordinate where the shear force diagram curve crosses the zero axis. Because shear is the rate of change for the moment, that zero crossing identifies the exact point where the bending moment reaches its maximum intensity. The point where the bending moment diagram itself crosses the zero axis is the point of contra-flexure. This is the physical location where the internal stresses transition from sagging to hogging. Locating this point mathematically requires setting the section's moment equation to 0. Pause here and solve for x using the equation 20x minus 5x squared equals 0. Mastery involves walking backwards up the calculus staircase. We can decode a complex shear force diagram in isolation to reveal the original external loads that created it. A sudden vertical jump up in the shear diagram translates directly to an upward point load, typically a support reaction at that exact location. A linear downward slope in the shear diagram indicates a constant, uniformly distributed downward load acting across that section of the beam. Any horizontal line on the shear diagram represents a zone where the shear force is constant, meaning there is no external load applied to that portion of the span. Navigating this staircase in both directions provides the core logic needed to decode internal stress translation in any determinate beam structure.